Okay, hello everyone. In this short video, I'm trying to calculate the electric field outside the charged cylindrical shell. So the question is, consider a uniform charged thin-walled right circular cylindrical shell having total charge of Q, radius R, and length L. So it talks about this figure. Determine the electric field at a point at distance d from the right side of the cylinder as shown in the figure. And there is a suggestion, try to help us. Use the result of example 23.2 and treat the cylinder as a collection of ring charts. So the first thing is, the question is about cylindrical shell. This figure is not a good representation of a cylindrical shell because it's shown as a solid cylinder. So please remember that this should not be solid. It's just a hollow cylinder, okay? Charged with a total charge of Q, has a radius R, and length of L. So first, it looks like the question asks us to refer to previous example. So actually, this example is something that we have worked on it. It's calculating electric field at a distance d, calculating the electric field at this point P, which is far from this ring. This ring has a charge Q and radius R. So we have done this example before, and it turns out that the electric field at this point, if we assume the ring is positive, the electric field will be to the right, and the equation for the electric field is given in the following expression, is equal to K multiplied by the d, meaning the distance between the point and the ring, and the charge of the ring divided by d squared plus r squared to the power of 3 divided by 2. Okay, now let's go back to our problem. Our problem, as we said, it's a hollow cylinder. So the best way, because it's a distribution of charge, so the best way to proceed, we need to divide this cylinder into many small pieces. So I'm going to show one of these pieces, and each piece represents a ring of radius R and of a thickness, let's call it dx. Okay, so to make things easy, I'm going to say this is the origin, and also I'm going to assume that the x-axis is going to the left, not to the right. It's kind of, I'm doing something opposite to the notation. So I'm assuming that this is x-axis. And the origin is exactly located at the point that we want to find electric field. Okay? Which obvious that this ring is far from the origin. So this is origin, 0, 0. So that distance is simply x. So the piece next to it will, you see that x keep changing. Actually, x changing from the first piece, which is located somewhere here. The first ring is located here. So x is equal to d. And the last piece is located at the very end of the cylinder, which is d plus L. Okay. So let's write the electric field due to this ring, due to the ring that we selected, this ring. It's actually similar to this example, right? So I'm going to use this equation. Okay? So now because the ring in this case is a small piece and carry a charge dq, so the electric field that's produced at point P will be to the right, similar to the ring, and I'm going to call it dE because it's produced by a ring, which is the ring is a small piece of the cylinder. So the dE is equal to K, I think there should be x here, right? We mentioned it, but we forgot to include it. So is equal to x, actually in this case, it's d, right? So it's d. So it's K multiplied by d, multiplied by dq, divided by d squared plus r squared 3 divided by 2. Okay. But that electric field is only the electric field from the ring which is a part of the cylinder. But we need to find the total electric field, which means we need to consider all other rings, the one at the very beginning, the one next to it, the one next to it, the one that goes all the way to the end. So we need to do integration, right? We need to do integration. Okay, so now it's very important, if we look at this description here, looks like we have a D, right? This is just D. I don't know why this became 2D or D. It's just D. D was a distance between the point and the ring, right? But the distance between, in our case, the distance between the ring and the point is X. So first thing, we need to change this D to X, right? One more thing. Here, again, the D was the distance between the point and the ring itself, which was D. But in our case, the distance, again, is X, so we need to change this D into X squared, right? The last piece, Q was the total charge of the ring in the previous example. But in this case, the total charge belongs to the cylinder. The charge on the ring is actually dq. That's why we put dq here. Okay, so I hope this is clear. Okay, in order to proceed, we need to do something for this dq. We're going to use the idea of density. So let me write the density of the whole cylinder. And as it's shown here, the cylinder, the charge is uniformly distributed over the surface of the cylinder. So I could write surface charge density of the cylinder equal to total charge of the cylinder divided by the surface area of the cylinder. Remember, the cylinder is a hollow cylinder, so the surface of a hollow cylinder simply is equal to 2 pi r multiplied by L. Okay, so this is for the cylinder. Let's write exactly the same thing for the ring, for the yellow shaded ring. Well, sigma for the ring is equal to charge of the ring, which is dq, divided by the surface area of that ring. But remember, the ring has a little bit, it has a thickness of dx, so I could say is equal to 2 pi r divided by dx. But you know that they are the same material, right? And they are charged with the same distribution of charge. So sigma is equal to sigma, which means I could say dq divided by 2 pi r dx is simply equal to total q divided by 2 pi r L, right? So we could cancel out 2 pi r, 2 pi r. Now dq, it simply equals to dx divided by L, which is the length of the cylinder, multiplied by q. Okay, so now I could substitute this into that term, and this is going to make things very easy. Okay, so the integration of the left hand side simply is equal to E equal to integration of, and I'm going to move this term into the numerator, so you're going to see why I'm doing that in a second. So this is equal to k x squared plus r squared 3 divided by 2. Okay, and we have L, so I'm going to write L here. We have dxq, q maybe I'm going to write it here. So we have dx left with the x, so this is going to be equal to x dx, and this has to be negative, right? Okay. So this is an easy integral, but first we need to know from where to where the integral, the limit of the integration. Well, you remember at the very beginning we said the first piece here located at a distance x is equal to d. So actually the first piece here we should write d. The last piece of the cylinder located at the very end of the cylinder, which is far from the point by a distance d plus L. So this is d plus L. And now let's do the math, okay? So it's obvious these two terms, it's inside a bracket, right? What's the derivation of these two terms with respect to x? It's simply equal to 2x dx. But we only have x dx, so I'm going to multiply by 2 and divide by 2. So the half, I'm going to just put it outside. So what's the derivation of these two terms? This yellow x squared plus r squared is simply 2x dx, right? Which means we know how to solve this. So this is equal to half. I'm going to move the constant k outside, l outside, q outside, and the integral simply is equal to so we have a bracket, we have two terms, and we have the exponent n, so it's going to be equal to n plus 1 divided by n plus 1, right? But minus 3 divided by 2 plus 1 is equal to minus half. Okay, so I'm going to bring this term down, so it's going to be equal to x squared plus r squared. And then remember, we have to divide by n plus 1, which is minus half. When you divide by it, so it's going to be minus 1 over 2, right? Sorry, minus 2. So it's going to be minus and 2 here. Okay. And of course, we have to substitute, put this d and l plus l. So what we do here, instead of x, once we put sorry, this is dl plus d, right? L plus d. So instead of x, we're going to substitute l plus d once, and then minus, and this one. So the equation simply, remember we have a minus here, so it's going to be minus k divided by l, q, and the rest is simply easy, is equal to 1 over l plus d squared plus r squared minus 1 over d squared plus r squared, and that's the final answer. To eliminate this negative, you could simply move this term to this side and move this term to the other side. Okay. Remember, this question has a second part. In the second part, we're going to do what? We're going to do the following. What if the cylinder was solid? How we could proceed? Okay. So let me summarize it. The procedure is very simple. This is distribution of charge. First, you need to divide the charge into many small pieces. In this case, the ring was the small piece. We used the equation of the ring. We did the integration. Okay. I hope this is an easy solution and this is clear. Thank you very much.